Okay, so this is with multigrid, and so don't have much time left. There are two topics. Let me just go over these two topics very quickly. So introduction to preconditioning. I think it becomes more and more important for you to actually know what preconditioning is about. I won't actually be talking about any particular preconditioners. Just want you to next time you encounter somebody using a preconditioner, you know what they're actually doing. Okay, so preconditioner is used in iterative method of solving ax equal to b. So a preconditioner says that instead of solving ax equal to b, I'm actually going to be solving I want to what should I say? So if I have a PL times A times PR, this matrix is easier to converge than A. So if I can find these matrices that make me easier to converge, I should be solving this system instead, right? So what I should be solving is PL A PR times PR inverse of X equal to PL times B, right? So this system is equivalent to this system, but this is hopefully easier to compute. So this is it's easier it converges faster. Another popular way to write a preconditioner is that let's focus on like one type of preconditioner. So if I have PR is equal to identity, I just have PL, right? So basically I have a PL times A times X is equal to PL of B. So if this is the case, it's beneficial to think of this way. If I have a PL approximately equal to A inverse, then my PL times A is approximately equal to what? Identity, right? So I have something like identity X equal to PL times B. It's if you use Jacobi, it'll converge in one step, one iteration. If you use Gauss-Seidel, it'll converge in one iteration, right? So there is it's beneficial to think of the preconditioner as like a approximate inverse of A. And if you're using a iterative method that only requires you to perform matrix vector multiplications. So for example, if you only have Jacobi, you can write it as x of k plus 1 times D, a diagonal matrix, plus L plus U, which is A minus D times xk equal to B, right? So that's another way to write Jacobi. So you can see that applying Jacobi only involves three things. One thing is multiplying A with a vector. Two is multiplying the diagonal of A with a vector. Three is multiplying the reciprocal of the diagonal with a vector to compute the xk plus 1, right? So this kind of iteration method, that's true for Jacobi, true for Gauss-Seidel, true for any Krylov subspace method. So if you have an iteration method like that, we just need to apply this PL times A to a vector. So PL A times xk, for example, is equal to PL times A times xk. So it only requires you to be able to apply this preconditioner. So you don't have to have a preconditioner as a matrix. You just have to know how do I apply it. And if my PL is an approximation to the inverse of A, then I just need to figure out a way to, so applying PL to this is like approximately solving AX equal to B, right? So how many methods have we discussed on approximately solving Ax equal to b? Jacobi, Gauss-Seidel, Krylov method, multigrid, right? All of these iterative methods are approximately solving Ax equal to b. So, right, so PL can be an iterative method. Right? Saying our X new is equal to multigrid of X, B, and N is like saying X new is equal to PL times PL times so with a 0 as the initial condition, it's like approximately solving PL times it's like PL times B, right? Because it's approximately inverting the matrix A. All right. And preconditioners, for example, is very useful in solving equations that are coupled. So for example, like one part of the equation has something like a Poisson's equation, but the other component is something else, maybe not even a differential equation. Right, so in like underground reservoir and simulations, you have a Poisson-like equation for the pressure, and you have advection equation that tracks where all the different components of water and things like that goes. You may have things like wells, faults, and things like that. So you have a Poisson-like equation, but you also have something else. Then using multigrid as a preconditioner just for the Poisson part is very, very powerful preconditioner. Okay, so this is basically for every iteration, for every outer iteration. For example, Jacobi or GMRS, you have an inner iteration of applying this PL, which may be one multigrid cycle. So the preconditioner, if you use a preconditioner, you maybe have an outer loop of let me give a procedure. If you have a program, you have a for loop IGMRS, right, for example. And inside the GMRS, you compute the residual. You actually compute AXK, and after you compute AXK, you apply multigrid. Basically, you for I multigrid, right? If you apply, let's say, maybe you just do one cycle, maybe you do 2 cycles. And in every multigrid cycle, you have pre-smoothing and post-smoothing. You have I smooth, right? That goes, of course, in our program, we wrote this as a function, but like you actually have these kind of iterations. So you have an outer iterative solver, and for the preconditioning, you have to apply the preconditioning every iteration. And in the preconditioning, you may have even inner iterations for applying the smoothers, right? So you have this 3-level iteration for just solving a linear system.